I think this is recording now. Okay, so the question was draw the lowest dot structure for nitromethane, right? That'd be okay, so nitro is NO2, methane is CH4. So you put those two together, you should get nitromethane, which is CH3NO2. Alright, so that's not a Lewis dot structure. That's a good place to start. So, if I erase this, where should you start with the Lewis dot structure? Carbon, okay. So that's C, H, 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 and then nitro is NO2, right?
Yep.
So that's N in the middle, right? And then the two oxygens. Okay, so nitromethane, they didn't tell you, but nitromethane is neutral, so there shouldn't be an overall charge. So we need to do something to make this neutral. Right now, this is neutral, but these should each be -1 as I've drawn them. So that kind of gives us a -2 charge. Something's strange, right? So how can we fix this? Double bond. So I'm going to erase these. Do a double bond. So what does that give me as a charge for nitrogen? Positive. And how about this oxygen here? The bottom right one? Neutral. Top right one? Negative. So that gives us nitromethane.
That's CH4 though?
So methane is CH4, right? And this is nitromethane. So that's where the name comes from.
What about the other H?
You don't have it. So in the nomenclature, in the naming of it, you just call it nitromethane, but you assume that it's 4 valence on carbon. So it's the formula is actually CH3NO2. But if you think about the naming, it's methane, nitro, nitromethane.
What I did was I double bonded both formals
Okay.
because I wanted to minimize all formal charges.
That would minimize all formal charges, but nitrogen can have at most 4 bonds. And so if you do another double bond here, you would have 5.
Yeah.
So that would give you.
I thought it wants 3 bonds.
Well, it wants 3 bonds, but it can take at the most 4. Yeah.
Okay.
Yeah.
Alright.
So this is the confusing part, right? So this is positively charged, but it doesn't want any more electrons. They can't take any more electrons. So it's kind of counterintuitive. You would think, oh, that's positive charge. You combine this together, you should go neutral again. But you would have 1, 2, 3, 4, 5 bonds to nitrogen. That's not allowed.
And then there's a second part to it. It says draw the Lewis structure for the conjugate acid.
The conjugate acid, okay. So what would be the conjugate acid? Eraser. Eraser? No? That's not it. Okay. Okay.
Just add an H to
I seem to have forgotten how to erase on this thing. I thought that was it. Alright, so I'm just going to make conjugate acid. So CHHNO plus minus. So conjugate acid would be this being protonated. So where can it get protonated?
Either one, yeah. So the one with a negative charge.
The one with a negative charge, right? So that means we would get rid of this, of that, and this would be the conjugate acid. And this would now overall would be positive. Why wouldn't it go down here? Right. So it has those lone pairs. It's kind of small. But they're not basic. Right. Good. All right. What's next? Blank page.
I can't get this because I didn't pay yet. And
Okay.
it's expired. I don't know what number it is, but I know we struggled with, do you remember the ones like the?
It was like determining, using the hybridization, determining which is the stronger acid, ranking
Oh,
the
yeah,
acids.
Okay. Was that in chapter 2?
Yeah. I think it was like number 16 or something like
Okay.
that, but I don't remember exactly.
Because we got it, but we ended up looking up the PKAs.
That's one way to do it.
But we know that's not the right way.
Yeah, but I didn't understand how to do it without
Okay, so something like rank the following organic molecules in order of increasing acidity.
Not my minute.
So this is an alcohol, a different alcohol, an acid, and then a ketone. Does that sound right?
Yep.
Okay. So the 5 that they give you are 1 CH3 CH2 OH. Second one is, I'll draw it the way they drew it, then I'll draw the actual structure. C6H5O5, sorry, OH. Does anybody know what that is? C6H5OH. That is phenol, or a hydroxybenzene, which I don't think we've gotten to, so I wouldn't expect you guys to know the answer for that. Then the third one is CH3CO2H. Is this looking right?
No, I think that was the next one.
Okay, I'll do this one anyways. I've already written it out. So this one I wouldn't expect you guys to know, A, because there's this in there. Because we haven't gone over that. So, which one should be the least acidic? Should be the worst acid on this list. Ignoring 2. Just ignore 2, just imagine it's not there. So you have an alcohol, 4, I'll also draw the structure of C, H, H. I ran out of room. This looks really bad. And that's another carbon there. So that's acetone. I guess also ignore number 4. Yeah.
So is number 4 the least acidic because it doesn't have like hydrogen bonded to polar, like it doesn't have hydrogen isn't bonded to oxygen, so it's not.
Yes, it should be the least acidic.
So is it least acidic number 4?
I think so.
Oh,
I would have to go look up the pKa on this one. So this one is another thing I wouldn't expect you guys to know. The acidic protons here are actually way more acidic than you would think.
the ones bonded to C are acidic?
Yeah, yeah. And so these are actually fairly acidic. I want to say the pKa is like maybe 9 or 10, somewhere in that range. So in water, that will have a really weak equilibrium value. Anyways, so ignore 4 and ignore 2, I guess. That makes it pretty easy. So between the alcohol and the acid, which one's the stronger acid?
Oh,
Acid.
The acid, right? Has acid in the name. So strongest. Alright, so what was the one that you were talking about? Was it a different hybridization states?
It had,
Yeah,
so there were double bonds and there was a triple bond and then there were some alcohol pairs.
The second part of the first one.
Let me find what they're on. So I have different questions, so it may not, let me just pause.
On this one, when I add the H to the O, with that number to O and the negative charge, take away the So does that mean I take away 1 electron or 2?
2.
I took away 2 and I said there.
Alright, I'll take a look at that one. There might be something with the drawing program on that, might not be recognizing it. Okay, so this is number 17 on mine. I don't know what it is on yours. So 1, 2, 3, 4. So H, this guy.
What number is this?
This is 17 on mine. I'm not sure what it would be on yours, but it's another ranking one. HF, CH3, and H2, and then 5 was CH4. Okay, so on something like this, if you have to rank stuff, I usually just pick the highest and the lowest. Those are usually the easy ones. The stuff in the middle is where it gets complicated. So what should be the strongest acid? HF. Okay, that has acid in the name. That's probably a good bet. So let's rank this. How to do this easiest. So I'm going to do it in a different color. So I'm going to say this is number 1. Okay. So what should be the weakest acid?
Isn't it that one on the far right, the CH4?
So somebody said this one, somebody said this one, or this one.
You want the weakest one, right?
The weakest one.
So that'll be the CH4.
CH4. Why is CH4 the weakest?
It has a pK of like 50.
Yes, it does.
The electronegativity is not
But-
really, the dipole moment is not very large.
The dipole moment on the CH4 is in this H and this H are approximately the same as far as dipole moment goes. So it's not dipole moment.
The sp3 orbital.
Right, it's hybridization.
Yeah.
Yeah. So the longer the bond, so this is where it gets confusing. So the longer the bond, the weaker the bond, but the longer the bond, the less acidic it is. So it has to do with your idea of bond strength. It's different from acidities. They're usually the same, but they're not always. So the weakest should be this. So there's out of 5, so this is 5. So that's the weakest. Okay, so I have a lot of colors I could choose from. Okay, black, Novia. So now we have to figure out either start going down from 1 or start going up from 5. So if it was me, I would start going up from 5 because I usually think of that being easier. So if you had to figure out which was slightly more acidic than 5, than this guy over here, which one would be slightly less acidic? Sorry, slightly more acidic.
The one that has the SP2?
This guy here?
Yes.
Yes. Right, so that one should be just slightly more so than this one. So that would be number 4. So to be honest, from here, either this guy here or this one here, it's kind of hard to tell. All right, so now we're in that middle range where things are kind of complicated. Now I know the answer because I've done reactions where these two things are involved. I know where the acid-base chemistry lies. But if you didn't, how would you predict which one should be the stronger acid?
Looking at the elements that
The elements that are in it.
The hybridization on the SP would be more acidic than the, even though the electronegativity on the nitrogen would seem like you'd pick that to be stronger, the hybridization would trump the electronegativity.
The hybridization would trump the electronegativity.
Like it'd be stronger, it'd be more acidic if it had the SP hybridization and less acidic. The nitrogen, the one that has the nitrogen would be less acidic.
So one way that I usually think of this is try to determine a reaction in which you can figure out the answer. So I am going to, how can I do it on this and actually have this work well? So So the answer would be, look up pKa. So things like this, things that are essentially apples and oranges, aren't exactly easy to compare, right? So you have something that's sp hybridized, you have something that's sp3 hybridized, but they're also different elements. So they're not similar enough where you can do a direct comparison to the two. And I would predict that this would be the stronger acid, right? Sorry, yeah. So this should be the stronger acid, this one should be happier. But I've ran this reaction before, and you definitely get this. So that's actually the more acidic one, and you wouldn't actually predict that. Which is kind of weird. So we wouldn't give you a question that would compare something like this and this, because they're just too different. Sapling would. But you also have the book to look up the pKa's in sapling. Which, does anybody have their textbook? I can look up those pKa's. Mine's in the office. Or Google. Google would probably have the answer as well. Somebody do that, and then somebody else give us another question to do. Yeah.
So you said that was more acidic because it's stable? Is that why?
This one?
It's happier being negative?
Yeah, if it had the choice here, having a negative charge on nitrogen or carbon, I would predict that the negative charge would rather go on nitrogen.
So if something's more stable, it's more acidic? Is that what it is?
If the conjugate base is more stable, yes. But the more stable the acid form is, the less acidic it's going to be. So essentially, you need to think about it as a reaction going to a product. So if you're asking the question CH3 and H2 going to CH3 and H minus, the more stable the product is, so this guy, the more stable the product, the more acidic it will be. So usually if I compare acids and bases, usually I don't even worry about the acid form. I just look at the relative stabilities of the conjugate bases, and that's how I figure out how acidic it is. If the conjugate base is more stable in one than the other, I'm going to say that one's going to be the stronger acid. What's next?
Number 5.
Number 12. What is number 12?
Number 12 is
This was what number again? Sorry, 16?
12.
12? Okay, 12. So it's asking what is the conjugate base, so conjugate acid. Conjugate acid of CH3CH2OH. So how do you figure out what the conjugate acid of something is?
Can you mix it with water?
can you mix it with water?
Like CH3, CH2OH plus H2O? Or does it have to be with?
There's even a simpler way of thinking about it.
Yeah, I just don't want you to.
So if you take an H off, is that acting as an acid or a base?
Or add an H?
It's acting as a base, right? So you need to figure out is what would be the conjugate acid of this. That would be if this was acting as a base.
So you add one.
Let me think. I'm confusing myself. So if that's the base, the conjugate acid. Acid.
Has one more hydrogen atom.
There we go. So I was thinking about this right, and then I screwed myself up. So the conjugate acid is the product as if you just added H plus to that. So if you added H plus to this, where should it protonate? It's not a trick question. It's the obvious place. Oh, exactly. So that would give you protonated ethanol. So what would if the question was base, conjugate base of that? What would you do? Take off an H. So minus H plus. All right. Curly arrows. So it's the way they drew it up on my screen looks something like this. Lone pair plus HCl. And that is going to H.
We have to know how to do this on quiz.
Tomorrow's quiz, no.
Okay.
The one after that, yes. Probably. Okay. So we haven't covered curly arrows in lecture yet, but they are tons of fun, I assure you. So the way to think about this is that curly arrows are showing the direction that the electrons are going. So they always go from something that's electron rich to something that's electron poor. Now they may be pretty picky on curly arrows. I am too. So there's a couple conventions that we follow. One is that if we have two electrons, we always use a double-headed arrow. So in other words, something like this. So if you had that, so if you just had just a kind of a fish hook kind of looking thing, that would be for radicals, which we haven't started talking about too much yet. And so anything that we do for curly arrows, you'll want to do like that. So basically a normal arrow. So if we want to take this, we want to figure out where the curly arrows should go. Usually in something like this, you'll know where it's going to. You'll know what the product is that you have to make. So in this case, what is the new bond that we have formed? New hydrogen bond, right? So it's in the way that I've drawn it here, it's this guy here, right? That's the new bond. So what we need to do is take the arrows and show how that bond got formed. So the way to do that is to take the electron-rich part, which is the lone pairs, these guys here, and then we're going to make a bond with hydrogen, like that. So the electrons are going to that hydrogen. And every time we draw a set of curly arrows, every time we do this, we're making a new bond. As it stands right now, with just this one arrow drawn, the product would have two bonds to hydrogen. Would hydrogen have two bonds? No. So what that means is we need to break a bond, and the bond is going to break and put those electrons onto chlorine. Okay? So essentially what that does is this is a new bond, and this is a broken bond. Broke. And so both are, I would say, equally important to draw correctly. You always draw it from where the electrons are going. Sometimes people will draw this with the arrow going the opposite direction. Okay? That's really common to do. Don't screw that up. And then here you always want to make sure that if you're making a new bond to something, you're breaking one, unless you have something like, if this was H+, if they just drew it as H+, then you wouldn't have to break a bond. So both you need. You need that one there, and you need that one there. That'll give you ammonium chloride. All right. What's next? All right, so the question was this guy. Wait, that didn't have an H. All right. So it was 1, 2, 3. Oh, and then there's like an ethyl group there. All right. Plus hydroxide, and the product is 1, 2, 3, 4. Plus O. Like that. So I'll just draw the lone pairs just to make ourselves feel better. All right. So again, we need to look at this and figure out which bonds did we make. What is a new bond in this product? That guy there, right? All right. So that's a new bond. So we need to make that. What bond did we break? Sorry, make. So the bond we broke is here, and then this one is new. So I drew the byproduct on this so that we didn't confuse ourselves. All right, so the byproduct is ethoxide. So the conjugate base of ethanol. Okay. So I'm not sure how Sapling wants it. They probably drew it the incorrect way. If they want it done in one step. So I will show you the correct way, and then show you the way they probably showed on Sapling. So the correct way would be that this would come in here. That would go up there to give you, I'll draw this carefully. Oh, this one we would not expect you guys to know yet. Kind of surprised they asked it. That. Can you see how those arrows give you this? So then what happens is we need to make a bond there for there. And then we need to lose this part here. All right, that needs to go away. So we just break it. And that gets you that. So that's the way you're supposed to do it. The way they probably showed on Sapling, what they're looking for in the answer, so I'm going to do that in red because it's wrong, is that they probably wanted you to do this. That's probably what they're looking for. That would be incorrect though, because that would be the wrong mechanism. So there won't be any curly arrows on the quiz tomorrow. Alrighty.
So I was just wondering if you could maybe draw like how the lone pairs go into in order to make it like SP2, if you could just like draw it, I don't know, maybe like more of like 3D, so I could like understand about the lone pairs, because that's kind of, I get that it's like SP2.
Yeah.
But whenever he was doing it in class, he kept like drawing like, if there's a pi bond, then you bring the P over, and then whatever's left is, there's an S and two P's, so then those go together.
Right, so let's start at the beginning, I'll say. So what is the hybridization state here?
SP2.
SP2. And these are the same, right?
Yeah.
I mean, they're by symmetry, they're the same.
Yeah.
What's the hybridization state here?
SP.
SP, right? Okay, so that's a good place to start. So I will draw this in 3 dimensions. Oh. They want to let me erase.
Why is carbon SP?
How many pi bonds does it have? 2. So SP.
Wait, yeah, I get confused from the book, how the book told me and how I was talking about.
So how is the book telling you?
Well, when there's a double bond, there's, so the SP2, I mean, it's just one pi bond, one single bond. There's a triple bond at the
Okay.
SP.
So question is CH3 dot. So why SP2? Good question. Why SP2? So, well, that's going to be loud. Let's take a look at the drawing of this. So I'm going to draw it as if it was SP3. So carbon, and then hydrogen, 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 and then here is going to be the orbital with its 1 electron. It's going to be sp3. And then we're going to compare that to sp2. Because those are kind of the 2 options. It's not like it's going to be sp, right? So it's got to be one of the 2. So I'm going to draw the carbon here with its orbitals like that. And so the thing to remember is that this is in a plane. So those are all flat. It's kind of hard to see here because it looks like that's kind of a plane too. You can draw the same thing. But this is flat, this is not. Maybe I'm not the best artist, but this is supposed to be flat. Okay, so why sp2? So the easy way to think of this is you have this pi orbital, right? In this case, we have a pi orbital. Here we have an sp3 orbital. We have 1 electron in that orbital, so either sp3 or p. If it's in an sp3 orbital, then it's going to be closer in distance to this hydrogen than it would be here, right? So this bond angle here is 90. That's 90, and this is 109. So in this case, it's going to be a little bit closer. I screwed that up. But these hydrogens are going to be 120. These ones are going to be 109. So if you think about it, this is exactly in between the methyl anion and the methyl cation, right? So it's somewhere in between. If this was 2 electrons, then it would be sp3 for the methyl anion. If it was the methyl cation, that would be sp2. And this is exactly in between the 2, right? It's 1 electron. It's not 2, it's not a filled lone pair, it's not an empty p orbital. So the answer that I would expect you to know is that it takes sp2. But I will say that for the methyl radical, it's less fixed in that. So for the methyl radical, it will kind of hop between the two. But it will spend most of its time looking more like an sp2. So the way that I think about this is that essentially what you want to do, since you have this essentially fairly empty, so this is almost empty, which is kind of the pessimistic view on things, but it's an almost empty orbital. So it's still not paired up, which means that it acts almost as if it was empty, rather than acting as if it was full. So since it's almost empty, this does not take up nearly as much space as if it was 2 electrons. So if it was 2 electrons, it would take up a lot more space, twice as much. And so essentially what wins out is that in the sp2, these are going to be 120, and these are going to be 109. And since the hydrogens are taking up more space in that 1 electron, they're going to repel each other more. So the way I think about this is that the methyl radical, or the cation for that matter, it all comes down to what the hydrogens would like to do. In this case, the hydrogens would rather be further apart here. They would be further apart than here. So that means if they had the choice, they'd rather be further apart. If instead it was the anion in blue, then those 2 electrons would take up just as much space, if not more, than the hydrogen. And so then they would rather do sp3, just like methane would. Is that clear?
I have
Yeah.
a question for you. In class, Dr. Wetzel was saying that when you have the radical, that since there's an unpaired electron, it's electron deficient, and so it wants to be closer to the nucleus.
Ah, yes, that's the way that he thinks about it. That's also correct.
Okay.
But
Because that's how I was thinking about it too. 'Cause
I mean, if that's the way to think about it for you, that's fine. It gives you the same answer, right? So the answer would be then that way is that, okay, this can be closer to here in the sp3 state. Sorry, I keep screwing that up. It's further away here. So that's 109, this is 90, so those two can be closer here, and so you get more benefit.
It like stabilizes, right?
It's stabilizing. But when I learned it through the repulsion. And so that's usually the way I explain it to myself.
Okay.
It's just as legitimate to go through this kind of explanation, the difference between the distances there. Ultimately, it gives you the same answer. But I like to think of this being the dominant factor, at least in my mind. Guess we have difference of opinion there. I mean, Dr. Wenzel.
Uh-oh.
It's all right. First tip. First of many, maybe.
Don't worry, I won't tell.
Is everybody clear on this methyl radical and stuff? The main reason that I have that caveat is that they will switch in between these two rapidly, the radical. And so you'll lose any information about what this thing looks like. It'll just pucker back and forth. So this is not very firm. So it'll jump back and forth between the two. But that's not really all that important.